Hi students, welcome to the video lecture 2 of heat exchangers. In the today's class, we are going to study the overall heat transfer coefficient for both plain slab and the cylindrical wall. So let us first study the overall heat transfer coefficient for the plain slab, whereas overall heat transfer coefficient is given by 1 divided by A into sigma of thermal resistance, where U indicates the overall heat transfer coefficient, which is already studied in the first module. So let us consider a plain slab. So this is the plain slab of thickness L. This is in the x direction. So let us assume that the hot fluid at temperature Ti is flowing at the left side of the slab, and whereas the cold fluid, which is maintained at temperature T naught, is flowing along the right side of the slab. So here the temperature Ti is greater than temperature T naught. That means heat is flowing from left side of the slab towards the right side of the slab, which is shown in the figure here. Heat transfer occurs from the hot fluid to the left side of the slab by convection with convective heat transfer coefficient Hi. Heat is flowing from left side of the slab towards the right side of the slab. Here, heat transfer occurs from the hot fluid at temperature Ti towards the left surface of the slab by convection with convective heat transfer coefficient Hi. Then from here to here, heat transfer takes place by conduction across the thickness of the wall L, and from outer surface of the slab, again heat transfer takes place by convection to this cold fluid, which is maintained at temperature T naught with convective heat transfer coefficient H naught. So here three types of heat transfer takes place. One is here convection heat transfer, from here to here conduction heat transfer, and then from here to this outside cold fluid again convection heat transfer takes place. That means here the thermal resistances are in series, that is convective thermal resistance, conduction thermal resistance, then again convective thermal resistance. Now let us remember the thermal resistance for the plain slab. Thermal conduction resistance for the plain slab is given by the formula L divided by K into A, which is already discussed in the module 1. Based on the Ohm's law, we have written this thermal resistance of the slab, that is thermal conduction resistance of the slab is given by L divided by K into A, whereas convective thermal resistance is given by the formula 1 divided by H into A. So now let us write the overall heat transfer coefficient, that is U, where U is the overall heat transfer coefficient. This U is equals to 1 divided by A into sigma of thermal resistance. I am substituting the values in this equation, where U is given by 1 divided by A into, this is the sigma of thermal resistance. Sigma of thermal resistance means addition of all the thermal resistances. So already I have told you here three thermal resistances are there. One is convective thermal resistance, this is conduction thermal resistance, and again this is the convective thermal resistance. Whereas convective thermal resistance at the left side of the slab is given by the formula 1 divided by Hi into A. Hi indicates inside heat transfer coefficient, convective heat transfer coefficient at the inside surface. If we'll consider this as the outside surface, inside surface, and this as the outside surface, so it is indicated by the formula 1 divided by Hi into A, where Hi indicates convective heat transfer coefficient at the inside surface, plus conduction thermal resistance 1 L divided by K into A plus 1 divided by H naught into A, where H naught indicates convective thermal resistance at the outside surface. So here in the denominator, everywhere A term is there. So I will take this A term as common. So if I will take A as common, then this A and this A gets cancels. So my final term will remain 1 divided by 1 upon Hi plus L divided by K plus 1 divided by H naught. So this is my overall heat transfer coefficient for the plain slab. Now, if the thermal resistance of the wall is negligible as compared to the other thermal resistances, then this term is neglected, then my final overall heat transfer coefficient for the plain slab will be 1 divided by 1 upon Hi plus 1 upon H naught, the unit watt per meter square degree centigrade, if the thermal resistance of the wall is negligible. So now next we'll study the overall heat transfer coefficient for the cylindrical wall. So this is our cylinder. So this is the inner surface of the cylinder. This is the inner surface of the cylinder, whereas this is the outer surface of the cylinder. So you can see here where Ri indicates the radius of the inner cylinder, where R0 indicates the radius of the outer cylinder. Whereas surface area of the cylinder is given by the formula 2 pi R into L. So already we know that overall heat transfer coefficient is given by the formula where U is equals to 1 divided by A into sigma of thermal resistance, or I can write this equation U into A is equals to 1 divided by sigma of thermal resistance. So now coming to this sketch, it is clear from this figure that heat transfer here also we'll assume that temperature Ti is greater than temperature T0. That means here hot fluid is there, here outside the surface cold fluid is there. So here heat transfer occurs from the hot fluid, which is maintained at temperature Ti, to the inner surface of the cylinder by convection with convective heat transfer coefficient Hi. And then from here to here, that is from inner and outer cylindrical shells, by conduction heat transfer takes place here, and again then to the outer cold fluid which is maintained at temperature T0, again by convection heat transfer takes place from the outer surface of the cylinder. So from here to here convection heat transfer takes place. From here to here conduction heat transfer takes place through this thickness of the cylindrical shell. Here conduction heat transfer takes place. Then again from the outer surface of the cylinder to this outside cold fluid which is maintained at temperature T0. Then again from surface of the cylinder to this cold fluid heat transfer takes place by convection. So here also three types of heat transfer takes place. Here from inner surface of the cylinder, from the hot fluid to the inner surface of the cylinder, convection heat transfer takes place. From here to here, conduction heat transfer takes place. From outer surface of the cylinder to the cold fluid, convection heat transfer takes place. So here also the thermal resistances are in series. That is convection thermal resistance, conduction thermal resistance, then again convection thermal resistance. So in case of cylindrical system, the area normal to the direction of heat flow is 2 pi RL, and this 2 pi RL, this area, it clearly varies with R. This surface area of the cylinder, it clearly varies with R. As R varies, the surface area of the cylinder is also going to vary. So therefore, while dealing with the cylindrical systems, we have to specify as to which area this overall heat transfer coefficient is based. Whether this overall heat transfer coefficient is based on the inner surface of the cylinder or whether to the outer surface area of the cylinder. First we have to specify it. So let us write the equation for overall heat transfer coefficient based on the outer surface of the cylinder, where U0, A0 indicates outer surface area of the cylinder, where U0 indicates overall heat transfer coefficient based on the outer surface area of the cylinder, where U0 into A0 is given by 1 divided by sigma of thermal resistance, and Ui into Ai is equals to again 1 divided by sigma of thermal resistance. This is the overall heat transfer coefficient based on the inside surface area of the cylinder, where A0 is given by 2 pi into R0 L and Ai is given by 2 pi Ri into L. So here also remember, for cylindrical wall, the conduction thermal resistance of the cylinder is given by the formula log R0 by Ri divided by 2 pi KL. So this is also standard. This is also written as per the conduction thermal resistance, how we have written for the plain slab based on the Ohm's law. So similarly, the conduction thermal resistance for the cylinder is given by this formula, whereas convective thermal resistance is given by the formula 1 divided by H into A. So now let us write the equation overall heat transfer coefficient for the outer surface of the cylinder, where U0 is equals to 1 divided by A0 into sigma of thermal resistance. So U0 is equals to 1 divided by A0, I will keep as it is. The sigma thermal resistance is nothing but the addition of all the thermal resistances. So this is the convective thermal resistance at the inside surface. This is the conduction thermal resistance. This is the convective thermal resistance at the outer surface. So here U0 is equals to 1 divided by, so here for each and every term it is multiplied by A0. So here A0 divided by Ai, where A0 is given by 2 pi R0 into L and where Ai is given by 2 pi Ri into L. So where 2 pi L and 2 pi L term gets cancels both in the numerator and the denominator. So my final term will be 1 divided by Hi in the bracket R0 by Ri plus log of R0 by Ri divided by 2 pi KL, where A0 is given by 2 pi R0 L. 2 pi L term gets cancels. So my final term remaining will be R0 into K plus, whereas A0 gets cancels. So my final term will be 1 divided by H0. So this is my overall heat transfer coefficient based on the outside surface area. So similarly, we will write the equation for overall heat transfer coefficient based on the inside surface area, where ui is given by 1 divided by ai as it is into sigma of thermal resistance, where inside this sigma of thermal resistance, it indicates addition of all the thermal resistances. The same equation we have written here, where ui is equals to 1 divided by, again here ai term gets cancels, so my final term will be 1 divided by hi here. So here ai divided by 2 pi kl, where 2 pi l term gets cancels both in the numerator and the denominator. So my final term remaining will be log of r naught by ri into ri by k plus 1 divided by h naught into ri by r naught by doing the simplification of ai divided by a naught. So this is my overall heat transfer coefficient based on the inner surface of the cylinder. So now here also, if again the thermal resistance of the wall are negligible as compared to the other resistances, that is high value of thermal conductivity K, or wall thickness of the tube is very small, that is ratio of R naught Ri by R naught is very small, which is equals to 1, and we are neglecting this term here. Ri by R naught term we are neglecting. If we will neglect this conduction thermal resistance, then my final equation will be overall heat transfer coefficient U will be equals to 1 divided by 1 upon Hi plus 1 upon H naught with units watt per meter square degree centigrade.